Go ahead and get started. Good afternoon, everyone. How you doing? Come on, this is a performance talk. I know it's just after lunch. Let's get a measurable response back here. Good afternoon. Perfect. There you go. My name's Tobin Titus. I'm a program manager on the Internet Explorer engineering team, and I'm focused on performance. Now, over the last several releases, the Internet Explorer team has been focused on making the browser fast. Now, in that time, we've learned a lot about performance, and we've learned a lot about the web runtime. But more importantly, we've learned a lot about how to optimize that web runtime around current and future web programming trends found in the real world. So, I know you guys love this audience participation. How many of you guys are here today to build faster websites or faster web applications? That's most of you. A couple of you are coloring or something back there, but I'll take that. So at past developer conferences, our team is focused on delivering a talk that provided developers with a list of things that they could do to improve their website's performance. We got a lot of positive feedback about that presentation, but one of the most common pieces of feedback that we got from developers was that they wanted to be able to measure the impact of our recommended site changes on their website's performance. So we heard you. And with Windows 8.1, we're providing developers with an updated Windows Performance Toolkit that provides you with the ability to do exactly that. No applause? Oh. So, with that said, we're not going to give you guys a list of things that you can do to improve your website's performance. Those talks are still available on Channel 9 if you'd like them. Instead, we're going to focus on the agenda you see on the screen. We're going to start off by defining performance. We've done that in the past. We're going to do it again. It's important for us to make sure that we understand what performance is and what performance isn't. And then we're going to dive in deep and give you a solid foundational understanding of the web platform architecture. And this will help you kind of develop a mental model of how your content flows from each subsystem in the browser until it's displayed on the screen. Last but not least, we're going to solidify that understanding even more by giving you a whole bunch of demos on the Web Performance Toolkit and showing you exactly how to measure the impact of any changes that you make to your website on performance. So let's go ahead and get started. So you're all on the hook. I know, again, you guys love the audience participation, and so I made you raise your hands and all that good stuff. And you're on the hook now because if you've thought about wanting to improve performance on your websites, you had to think about performance at some point, and I'm going to test that knowledge. So here's your scenario. I live in Seattle, and like many of you, I had to travel to San Francisco to come to the conference, if this will work. So I bought round-trip plane tickets. It's really slow. And bought the round-trip plane tickets. And in order to buy those tickets, I visited 5 popular travel websites. Those would be Priceline, Kayak, Travelocity, Expedia, and Orbitz. So as I started visiting these sites, I noticed that they all had very similar looks and feels. They all had very similar functionality. So up in the upper left-hand corner, you'll find logos. You'll find banner ads on all of them. They all have some edit fields like where I'm coming from, where I'm going to, what are my start date, my return date, and they're all running some sort of analytics. So as I look through them and they all have very similar looks and feels and very similar functionality, I assume that they're going to all have very similar performance characteristics. So instead of booking my travel right away, I did what any perf guy would do. I measured them all to see which one was fastest. And this is the data that we came up with. We're going to anonymize the data. We don't want to pick on anybody today. But this is the data that we have. And we can look at the data for each one of these websites across a number of dimensions. The first dimension, of course, is the total download size. If we look at the total download size, we see that it varies pretty significantly. Site number 3 has 1 megabyte, and site number 1 has 3.7. That's nearly a factor of 4 in difference. If we look at the total number of constructed DOM elements, Again, that's going to vary. And it's nearly a factor of 4. Actually, it's over a factor of 4 at this point. For the CSS rules, we see, once again, that we go from 1100 to 5300. That's nearly a factor of 5. On images, we go from 6 to 66. That's pretty significant. That's a factor of 11. Now we're going to look at the total number of formatted script lines. And this is pretty significant as well. We have 10,000 on the low end and 77,000 on the high end. So again, that's almost a factor of 8. And last but not least, we can see that each site chose different script libraries and different architectural ways to construct their page. So take a look at the site. You're all performance gurus at this point. And tell me which one was fastest. Who's guessing? Okay. Who's guessing 4? Who's guessing 5? All right. So it's site number 5. Site number 5 is fastest, but a lot of people will guess number 4 because they look at the total amount of script, and they'll usually equate script lines with performance. They figure all that script has to execute somehow, so it must be the fastest. So look at it one more time and tell me which one's the slowest. How many are guessing 1? 2? 2 it is. Now 2 is the slowest, but again, just to reinforce that point, script lines are nearly the same amount as the fastest site that we had on the page. It doesn't have the most number of elements, it doesn't have the most number of image files, and certainly not the most amount of script of any of the sites. But yet, it was the slowest. So what am I getting at? Performance is not the measure of how much script you have, or how many elements you have, or how many downloads you have. All those can come into play, but really the measurement, or performance is really the measurement of time and efficiency that it takes from the point that a user makes an interaction on the page, until that result of that interaction is displayed on the page. So that could be either a navigation, that could be a dialogue that's popping up, or some sort of animation. So these are the 3 factors that influence the major contributors to your site's performance. Networking, obviously. Networking bandwidth and connectivity play a significant role, as we'll find out later. Most people don't think, well, most people will think about that, especially at conferences like this, where everyone's sharing Wi-Fi, and that's an important part of performance for any page. CPU, many people equate CPU with how fast your machine is. If they say, my machine is slow, they're usually referring to the CPU. But one thing that most people don't equate is the GPU. And the GPU is very important because if you think about it, anything that's put onto the screen has to go through the GPU first. So the GPU becomes a very significant player in your website's performance. So how do we control these? We don't typically think about hardware level abstractions or hardware level. We're thinking about changing CSS or adding DOM elements or something like that. We're not really thinking about the hardware. So how do we improve our site's performance? Well, if you can read ahead of me, that's really understanding the web runtime architecture. And the web runtime architecture and how you understand that and how you form that mental model in your head and how things are going to execute on your page really will impact how those 3 resources are utilized. So this is the way that we tend to think about the web runtime. Now, I specifically say the web runtime because everything that I talk about today is going to apply to every modern web browser. Now, we might have different names for our subsystems, and we might have different architectural boundaries. But at the end of the day, every web browser has to do the same things. And this is the way that we think about it. We tend to think of it as a number of subsystems and a pipeline that your content runs through, from the point that a user types a URL into the address bar until that content's displayed onto the screen. So we're going to walk through this really quick. Once we request a page, we go through the networking subsystem. And the networking subsystem is going to go up to the server and download that initial page to the client. Then we're going to pass that off to a pre-parser, and that pre-parser is going to sprint through looking for any additional sub-resources that we're going to need. Now, those things might be script, they might be CSS, but there are additional resources that we know that we're going to need before we can render the page to the screen. So once we get those requests, we issue those back to the networking subsystem, and we're back there again, and we're downloading content. So we download all of our content to the client. Once we have that content, we're going to pass it off to parsers. And we have dozens of parsers inside the browser. We have XML, HTML, we have XHTML, CSS, JavaScript, SVG, and different variations on all of those. So it's really important to understand that, again, the amount of content that you have to parse can play a significant role as well in your page load time. But mainly the parsers are responsible for creating internal data structures. And we're used to a couple of these internal data structures, one, of course, being the DOM. You guys are familiar with the DOM tree. These are things this is just a hierarchical representation of your markup in code. And then, of course, we have the CSS cascade. The CSS cascade is just your styling information, all the information that we're going to use to format the page. We'll talk about formatting in a moment. Then we have the JavaScript sandbox down here. And poor lonely JavaScript, it gets all of its content, and we download it into that sandbox where we do our parsing there. Parsing for JavaScript happens in the sandbox. Bytecode generation happens there. Native code generation happens there. Everything happens in that JavaScript, and it can't get out. It's stuck in there, except for two ways. We can get out of the JavaScript sandbox by first using DOM APIs. These are things like getElementById, appendChild. These are all the things that we use to program our page for animations or even just to load content dynamically. The second way is by issuing requests back off to the networking layer through XHR. So if we think about content dynamically loading content after our initial page load happens, we go off and we issue an XHR request. We pull additional content back down inside. It goes into the JavaScript sandbox, and we execute from there. Now, of course, the content that we download, that can be used to manipulate the DOM tree and manipulate the CSS. So we start to see that part of the pipeline come together. Then we move off to formatting. So formatting is this. The DOM tree has no understanding of width, height, z-index, or position. All it knows is its parent-child relationships in that DOM structure. So we have the CSS cascade, and we have the DOM tree, and we just have to map those together. So that's all that formatting is doing. And at the end of that, we have this sort of intermediate state of the tree that holds all of our information that we can then pass to layout. Layout's responsible for saying, I have all of these DOM elements, and I have to put them onto the screen. So, you can think about CSS as a block-based layout system. It's inherently a block-based layout system that makes everything on the screen a block. So if it's a paragraph, it's a block. If it's a image up in the upper left-hand corner, that's a block. And somehow, if it's a circle on the screen to the browser, that's a block as well. So everything's a block. And we have to figure out how to construct those blocks, and that's what layout does. And then the other thing that CSS is it's a flow-based layout engine. So if you think about Microsoft Word or any word processor out there, as you're typing and content wraps around and flows, layout also has to do this. It has to figure out where your content's going to be, and if it's too big to fit on the screen, whether it needs to wrap around or if it's absolute positioned, it needs to put those in the different places. At the end of that process is the display tree. We get this display tree, and it's not a one-to-one mapping between the display tree and the DOM tree. And a lot of people get confused over that. But essentially, you think about, you might have DOM elements that have display none marked on those. Those aren't going to show up in your display tree. Vice versa, you might have things in your display tree that weren't in your DOM tree. A good example of this is a list element. So if you have list elements, your markup has no idea what the numbers 1, 2, 3, and 4 mean. Those get added inside of formatting and layout. And in the display tree, we then have to account for the additional font and the spacing that it takes to add those numbers into your list. So this is the display tree, and the display tree is literally all the instructions that we need to paint to the screen. So we have all the information we need to go ahead and start painting. And that's obviously the next step. But we're not going to do painting right away. This is just the stuff I specifically say that we're ready to paint to the screen. Well, we paint only when we get a hardware interrupt that tells us we're ready to paint. The monitor can only physically paint a number of times per second. And this is usually your refresh rate that you're used to seeing running at around 60 hertz. And this is where we get that magic number of 60 frames per second. We can refresh 60 times per second if we're at a refresh rate of 60 hertz. So as soon as we get a hardware interrupt that says we can paint now, we go ahead and take all the display tree information and we paint that to surfaces. In IE, on Windows, we're painting to DirectX surfaces. The next step, of course, is composition. So we have all these surfaces, and we're passing those off to the GPU. And now we get to compose those all together. And so we hardware accelerate our composition of laying blocks over where they need to be or positioning them how they need to be. So that's the pipeline of how your content gets from one side to the next. But the other piece that we need to talk about is really just input. So if we look up here, we've got touch, we've got mouse, et cetera. And we tend to think about those as coming in backwards through the pipeline. We don't bring them up through the pipeline, how the rest of the content flows. They tend to come in backwards. So if you think about your mouse or your cursor is clicking on something, we need to do hit testing and determine where we are on the screen and work backwards to get back to the DOM and figure out what's under that screen and whether we need to fire JavaScript or not. So this is the pipeline. This is the web runtime. This is how you can start to think about how your content flows through the system. But more importantly than being able to form that mental model is actually being able to see it in practice. So how can we do that? Luckily, we have ETW. ETW is simply a lightweight logging mechanism offered by the operating system. I'm not going to get into details about this. We have a couple other sessions that might go a little bit deeper. But in general, we have these controllers. And these controllers are simply responsible for spinning up providers or starting up providers to start listening for events. IE is heavily instrumented, so we're firing off these trace events that allow us to then write them to buffers. So when our controller starts them up, we start listening to certain providers, and we write all the events that those providers are listening for to a session buffer. That session buffer then, when we're done listening, writes off to a trace file that then we can analyze with our consumer. Now you can write those controllers and your consumers yourself. There's plenty of documentation out there on how to consume those. But luckily, as I said, Windows 8.1 provides us with an updated Windows Performance Toolkit that allows us to do really, really powerful analysis of all of that trace information. So you can get all this information. This slide will be online, so you'll be able to get to this link where you can download the Windows Performance Toolkit. And there's also a blog post with information on how to use some of our old tools to do performance analysis. We'll update that link to point to the new location once we have new blog posts. So this is the Windows Performance Toolkit. We're going to dive in deep with these demos now, and we're just going to show you how the Web Performance Toolkit or the Windows Performance Toolkit exposes that web runtime. Oh. Perfect. All right. So how many of you guys have seen the IE test drive? Great. The IE test drive is really where the engineering team gets to have a lot of fun. As we're building new features, we go out and we build these demos to show off some of our features or show off performance. And we get the opportunity to have a little fun. And some of these I think you saw at the keynote. You saw our levitation demo with WebGL, which is really cool. But this is where we put all of our demos. One of our earliest demos was flying images, and I'll bring that up here real quick. So this is just a flying images demo. It's one of the first ones that we put out there. It's basically an HTML4 demo. It just has a whole bunch of images on the screen, and if you look, I can kind of move those images around, up and down, just with the mouse. And I can actually increase the number of images that are on the screen or reduce them. And in the upper left-hand corner, you'll see frames per second and the number of images that are actually being drawn. Up in the upper right-hand corner, you'll see some options that we can toggle with just buttons that kind of look like links. And so this was one of our early test drive demos. And the way we're going to show you the web runtime through the web Windows Performance Toolkit is we're going to strip everything out of this demo. We're going to take everything out, the JavaScript and the CSS. We're going to do a page load, and we're going to measure that. And then we're going to start adding things in. We're going to start adding animations. We're going to start doing some bad practices so that you can see what a bad pattern looks like as well. And then after that, we'll point you to some other talks that will dive in even deeper with these tools. So this will give you a good start. Okay. So in order to take a trace, let me go ahead and pull up my list. These are all the demos that we're going to walk through today. In order to take a trace, I'll show you what we do. We basically start up our Windows Performance Toolkit, and I can bring that up. I've just stored mine in a directory called WPA. When you install the Windows Performance Toolkit, you'll get links to them on your start screen if you'd like. But for me, I just like running these from command line. So I'm going to start the Windows Performance Recorder UI. Now this is just a UI that allows us to start our recorder. If you remember back at that slide, we had controllers. This controller is just telling us what providers we want to listen for and allowing us to go ahead and start taking a trace. I'm going to go ahead and expand that, and you'll see that we have scenario analysis here. I'm going to do HTML application analysis. That's what we're interested in. And I'm going to change this detail level to light. So we just start taking light traces. So I can go ahead and hit start, and I can go run one of my demos. We'll talk about this in a minute. And then we're going to go ahead and hit stop here. Save. You type in a description. You hit save. And once it's done saving, you can then open it up in Windows Performance Analyzer. So you see the button changes to open in WPA. I'm going to do this a little cooking show style. I've already provided all the traces for each one of our demos, so we're going to look at each one, and we're just going to open the traces that I took beforehand. But you could open here in WPA, and you'll see that it opens up. What you get when you open Windows Performance Analyzer is you get graphs over here on your left, and then, of course, you get a blank screen over on your right. Now, you can drag whatever graphs in that you find interesting into your analysis view, and I'll show you what that looks like. You simply expand something that's interesting, and we'll show generic events, and I can drag that in. So I just drag it over, and you can see already there's a ton of information in here. Now, if you remember, I said there's a number of providers that we have that are writing events off, and these are all the providers here on the left-hand side. So if I just zoom in a little bit, you can see that you can see the events there. You can see the providers. In fact, if I expand that a little bit better and turn off the column names, you can see again there's a lot of providers here. And those are just the ones that we turned on with our trace. So this actually scrolls in infinitely. You see all these events? I can just keep scrolling in, and there's tons of information in here. They're just all clustered together. And these, the amount of time measured between these are just, microseconds, nanoseconds. Just small amounts of time between each one. So I'm going to go ahead and close this, and I'm going to open up our first trace that we took beforehand. And I can do that through the command line. Actually, before I do that, I want to go back and talk a little bit about this view that you have here. This is the same demo that I ran just a minute ago. Promise you, it's the same demo. We don't have any CSS, we don't have any JavaScript, so this is just what the page looks like. And if I open up the code, you can take a look at the code here. It's very simple. This is just my very semantic markup. You can see buttons here, like I said, in the upper right-hand corner. Those were all the buttons that changed options. So there's no event handlers hooked up to those because we disabled JavaScript. These are the gauges that you saw, the FPS meter as well as the image meter. So we'll see those up there. And, of course, our JavaScript down here at the bottom and our CSS at the top. So this is what that page looks like. For this particular view, we went ahead and commented out the JavaScript and the CSS. So page load, if you notice when I hit refresh here, takes almost no time at all. In fact, you can't even see it spin up. It's just done. So I'm going to go ahead and load that inside of WPA. And again, I can do that from command line, or I could just open up WPA and do File Open from the menu. So I'm going to go ahead and open this. So again, the same view that we got before. I'm going to go ahead and open up a couple of charts that are interesting to me. The first one is the vsync. Now, if you guys remember, I told you that the vsync was the hardware interrupt. And this is how often we can paint to the screen. So if we actually zoom into a section here, just zoom in a little bit more with Control mouse wheel, you can actually measure that distance. And this is a that amount of time. It's a very common amount of time that you see between these is 16.66 seconds or 16.67 seconds. And that's what most people are used to doing. We'll get to questions afterwards. So, this is just the amount of time between each of the vsyncs. So this is the hardware interrupt. So we'll pull that in here. Now we'll pull in the window in focus. Window in focus is kind of interesting because we get to see what was in focus during the entire time of our trace. This wasn't just what happened inside of IE, but this is from the time that we hit start until the time that we saved that trace. So we see over here that we had the WPR was in view. We tabbed over to Internet Explorer, and then we went back to our WPR to save the trace. So really the relevant piece of information for us is just inside of this portion. Now I'm going to click up here in the upper right-hand corner. I'm just disabling the table. All I'm interested in is the graph. You notice I can resize these very easily. But one of the other interesting pieces, you'll notice that anything that I select is actually selected in every single one of the charts. So I selected the Internet Explorer time piece, or time section here, and I right-click and I can zoom in, and I'll zoom in on all the charts that I've dragged over there so far. So this might get a little bit tedious after a while, where you're opening up one trace or another trace, and you've dragged in charts and resized them and all that, so that gets very tedious. Once you've got all the charts that you want, you can then just go to Profile, Export, and you can save that trace out to a location that you can then go later and say Profile.apply, browse to it, and select the traces, or select the profile that you're interested in. And I'll show you, this is what we're going to use today. So now we have all of the charts that we'll use throughout the rest of our analysis. So I just want to walk through these charts really quickly. We have, of course, the vsync that we walked through. We have the window in focus. This is our WinINet download, so this is all the information that we downloaded. And you can see it went very quickly here. And then we have our CPU utilization down here. So this tells us this matches up all of the CPU time to that pipeline that I showed you earlier. So if you think back to that PowerPoint slide where we showed your Windows runtime, these match up precisely to those as well. So I'm going to go ahead and zoom into this section. This seems to be, if you look at the CPU utilization down here, this seems to be our relevant page load time. I'm just going to go ahead and zoom in. And you can see what's being downloaded. Here's our HTML page. And we can see immediately after we finish downloading, we then go into parsing. I'm just going to zoom in a little bit so you can see that. Oops. So we can make this bigger. And we can get rid of this. So that should give you a better idea. Once we're done downloading, we can go ahead and start parsing our page, as we talked about before. So we had our networking, then we have parsing, and then we have layout. But some of you are thinking back to that slide, and you're thinking, wait a second, where did formatting go? We have formatting. Because I remember specifically, you have your DOM tree, and then you have formatting, then you have layout, and then a display tree. Well, the one thing we took out of here is there's the CSS. We don't have any CSS in here, so there's no formatting to be done. We simply go into layout. Right after that, we'll go into display. So you notice these two colors here, both green and red, and these are actually part of the same process. If I zoom in just a little bit so you can see better, when I go mouse over the green, you'll see a little section here, and I will zoom in so you can see that a little bit better. You can see where it says root/trident/display. That's basically the root part of the display in what we're tracking. And if I mouse over the red and zoom in here, you'll see it's root/trident/display/view/render. They're part of the same process. You can think of the red as sort of a sub-process inside of that. And when I talk about display, I'm talking about those last two pieces of the pipeline, and that's painting and composition. So if we back out again, zoom out, and just look at this page load, we have our networking that comes in, and then we have our parsing, then our layout, and then display. It's very quick. As a matter of fact, if I measure this time, I'll even include the download here. But we're at 19 milliseconds. So it's basically less than a frame, or just over a frame. If we take the portion from the time that we finished downloading our HTML page on, that's at 15 milliseconds. So again, less than a frame just to download and display everything. It's pretty good. So now I'm going to go ahead and show what happens when we add CSS. So if we go back to our list here, I'll go ahead and edit the page. You can see, well, I've already edited this one, and I've got CSS enabled. And if I click here, you'll see that the page has changed significantly. All of our buttons are now looking more like links up in the upper left-hand corner, or your upper right-hand corner. And the FPS meter and the image meter are there, but there's no content inside of them. So this is just all the CSS being loaded. And there's one other big piece there, and that's the background image. That background image is now coming out of our CSS. So our CSS loads a background image for the page, and now we get to see what that looks like inside of a trace. So it can also get a little bit tedious, as you'll notice. I've opened this up, and I don't want to have to go to Profiles and Apply every time I go and open a page. So I'm going to go ahead and do that once. Every time I open a trace, I want to get this view. So if I just go to Profiles, Save Startup Profile, now every time I open a trace, this is what I'm going to get. And this allows me to save a little time. And once you find a view that's suitable for you, you'll probably set that as your startup profile as well. So I'm going to go ahead and close the vsync well, actually, I'm going to close the window in focus after we zoom in on the Internet Explorer portion. And then we see the WinINet downloads. We also see here this other view I haven't talked about much, which is just to the GPU. But you can see that the GPU spike happens here right towards the end. We'll see a few smaller spikes in here. This is usually happening on the vsync or drawing or painting something. But you can actually see the GPU utilization, and it's very minimal in this case. So we're going to go ahead and close that for now. I'm going to go ahead and zoom in here and make this a little larger so we can see it again. And now let's concentrate on this page load. We have a couple interesting things happening. First and foremost, you'll notice, I didn't point this out last time, but I'm going to do it this time. As we start to load our page, you'll notice that we get a little bit of layout here. And a lot of people ask about this. Why are we doing layout? It's because we're clearing the DOM tree. We're clearing everything out. We're getting rid of the display tree, preparing our content for the next load. So we know that we're going to get new content to draw, so because we're downloading, so we're going to go ahead and clear that out. Then, of course, we're going to start parsing as soon as we get our HTML through. And when we're parsing our HTML, we find this CSS file. We start parsing the CSS file down here. We continue parsing the rest of the page, and then we go ahead and do a small amount of layout. Now, we know that we can do some layout here, so we go ahead and do that. But I want to zoom in here to this section because this is very relevant. You notice what we get is we actually do layout, and then formatting, and then layout. And I told you in the slide that we do formatting, then layout, then display. But what's happening here is actually layout is what owns the display tree. So layout owns this tree, and what we're going to do every time we're ready to draw is we say, hey, or we're ready to lay out, we'll ask layout, do we have a clean display tree? And layout will say, no, we don't have a clean display tree. We have to go do formatting. We just got a whole bunch of CSS information, and we have to do this formatting. So then we go do our formatting. We update our display tree with that information. Then we continue to lay the rest of the page out. So this is what's happening on the basic. Anytime that we see formatting, we should see a small amount of layout right before that, and that's just us asking layout if we have a clean display tree. Next, what's happening is after we do that layout, you'll notice that we get this long gap. And this gap is, 6-7 milliseconds? And it looks like there's no work being done. In a performance world, 6 or 7 milliseconds is pretty significant. So you have to ask yourself, what's happening here? Well, the web is inherently single-threaded. We've said that before. We'll say it again. The web's inherently single-threaded. Now, there's some things that we can do in parallel, and one of those things happens to be image decoding. If you remember, on our CSS page, now we have this really large background image. And so what happens is we kick that off, but we really can't paint to the page, which is what happens next in this display section. We can't paint that page until we have our image downloaded. So, downloaded and decoded. So we can see we've got it downloaded. I'm going to go ahead and pull in one other view under computation. And this is the known thread CPU breakdown. I'm just going to pull this in for this. And just to match it up, you can see that I can set the interval here for how often I want to, how big my intervals are for the slices. Now I can see the CPU activity of every thread that IE cares about. That's DWM, that's the decoder, that's the DX scheduler, and of course the IE/UI thread. Now this IE/UI thread is exactly the same information that you'll find in here. As a matter of fact, if I enable this guy and turn all of this off, you'll see that the scales and the amount of time look pretty much the same. The difference, of course, being, I can just go ahead and disable some of this. The difference between this and this is now I can see when decoding is happening. So what happens is I go ahead and start to lay out the page, and I realize as I'm laying out that I need some information about that image. I've downloaded it, but I don't know how large it is. So I start to decode metadata. As I get that metadata, I can go ahead and display to the page. I know how large that image is going to be, so I can prepare the surface for that. And then once we're done laying out, you'll notice that I decode the rest of the page. So we've decoded metadata. Now we're going to decode the rest of the image. And so we're decoding that. And then once we've finished decoding, you'll notice there's still a small gap between when we finish decoding and when we can actually display to the screen. This is because now that we finished decoding, we have to push that image to the GPU. There's work that has to be done there to push that to the GPU. So we finished doing that. We're going to push it to the GPU. And then there's one other thing that's happening there. And that's that you see what the vsync comes in. We finished decoding. Our display tree's up to date. We push this thing off to the GPU. And now we hit our vsync. And we say it's time to display. So we hit that vsync, and we start doing this large chunk of display. And you can see that this display takes a while compared to our former display. And that's just because, again, this is 28 milliseconds there. It's a significant amount of time just for display. And again, that's because it's a large image. If you go back and you look at that, it's a couple meg, that image. So our previous page load time was about 15 milliseconds if we didn't count the download, the initial page download. So we'll measure this after the download there as well. And we can see that we're at about, let's see here, 90.6 milliseconds. So just adding that image is a pretty significant cost. So again, the added pieces here that we're actually doing CSS parsing, we're doing formatting that we didn't do before, and then we're doing our display that takes longer, and we're doing image decoding. So now we've done that. Let's go ahead and add our JavaScript now. So if I go back in, you'll see again, I've already commented this out, but you can see adding JavaScript looks like this. Now, we're not doing much in this JavaScript. We're actually just loading it and doing a very minimal amount of work. If we look at the JavaScript code, you'll see at the very bottom I have a add event listener. And this is just a load add event listener that starts setting up our revealing module up here. If I go into a setup, let's try that again. There we go. This is setup. Setup is just going ahead and saying set document references. And you see here that's just calling getElementById for all the buttons that we're going to hook up event handlers for. Then we go ahead and hook up the document events. Again, add event listeners to all of our buttons. And then we're setting our image sources. Now, we're not actually setting image sources. We're just setting the paths for all of these in there. And then we call, at the bottom, you'll see that we call draw or get bounds. We go ahead and we cache the values for the size of our browser, and then we create our board, and then we should call draw. But I've commented that out. So the only thing that we're getting out of here is we're getting the number of images on the screen, and that's coming from our setup up here, which is a start count. Start count is actually just a one-dimensional side of a matrix. 2 times 2 is 4, so we have one side is 2 images. So all in all, you can see that we're just loading the JavaScript, and we're not doing much with that JavaScript once it's loaded. Let's go ahead and look at that in a trace and see what that looks like. Now you'll notice that, again, I set my startup profile so I don't have to go set it this time manually. Once we're done loading that, I can go ahead and zoom in. And here again, you can see we got the window in focus. We started loading our page. I'm just going to zoom into this section. Really, it looks pretty much the same as our last one. I'll just get rid of some of these so you can see a little bit better. It looks a lot like our last trace. We still have this large gap here between displays. And then we have some JavaScript that's executing in here. So we'll see orange that happens. This orange, again, these colors happen dynamically. We're not guaranteeing that every time you load this trace, you're going to get the same color, unfortunately. So you kind of do have to look through. Once you've done looking at traces, you really don't need the colors. You kind of know what's happening just from looking at them. But this is JavaScript. And we'll see that JavaScript is loaded here, basically, once we start parsing. I'll go ahead and zoom this in again. See that we do some JavaScript parse source. Then we do some bytecode generation. And then we do our JavaScript execution. And we're going to execute that as soon as we're done downloading it. And then once we've done that, we've done our basic layout, we're going to see JavaScript execute again. And this is because we have an onload event handler. So our JavaScript onload event handler starts executing at this point. So you can start to see that this is a basic clean page layout, or clean page load. There's not a whole lot happening here other than just getting our resources, and of course you can see the resources coming in here, and then displaying them to the screen. So if we measure that time again, just want to see the difference here. We're at about 89 milliseconds. Still not bad. So now I want to look at sort of a bad practice. We've looked at loading a clean page. Now let's look and see what happens when we look at a typical page load. Now, if you remember back to our analysis of all those sites, we had a number of script libraries. We had one page that had 77,000 lines of script that was loaded. So what I'm about to show you isn't all that unheard of. We actually see this more often than you would think. I'm going to add a whole bunch of script to the page. I'm just going to go ahead and add all of this script. And actually, I'm going to add all of this CSS as well. Now, these are some common scripts. We'll see things like Modernizer, jQuery, Prototype, Scriptaculous, etc. And then down in the CSS section, it's slightly contrived, but not so much. So we'll see jQuery UI and YUI together a little bit. We're adding some, and I say slightly contrived because I'm adding the UI Light and UI Dark CSS that we'll find inside of WinJS when you're building a WWA application. So I'm adding them both. The page is going to look really ridiculous, but I just want to give you an idea of what a page load looks like with all of this content inside of it. So if I go back to my HTML page, just paste this at the top, save that, and then this is what it looks like. Kind of back to what we had before, except for really dark and centered. So, but there's a lot of content inside of this. You saw what a clean page analysis looked like. Let's look at this one with a bunch of JavaScript and CSS. Make sure I got that. Yeah. So this gets really, really fun. So if I zoom into this section, you start to see, you don't really need to know what all the colors are doing, but you can see the toggling between one color to the next, back and forth, between loading JavaScript, loading CSS, parsing HTML, going back to loading some more JavaScript, etc. It's not a clean load anymore. We're no longer just loading all of our content and going, and that's because we've put everything up here in the head, and those scripts might dynamically inject some content into the page or modify attributes. And so we have to go back and add those into the DOM tree. And then we account for those on our next pass for layout. So all of this starts to play a toll. And you'll see just with that payload that I had, as I start to measure the impact of that, we'll actually go out to here. This will load dynamically. We're at about 700 milliseconds. So you still think, well, that's not bad. But if you think about the factor involved here, again, there's not a lot of DOM involved here. This is really just your script and your CSS and a small amount of DOM. And we've got 700 milliseconds. That's actually pretty significant for a page load, especially when you're loading from the local host, like this trace was. So the factor here is somewhere around a factor of 3 or 4, just to add all of that script. But this doesn't just affect your page load. This also affects animations. So if you put animations on the page, you've got all this extra CSS information that you put in the CSS cascade. On your next formatting pass, the next time that you have to put that CSS and that DOM together, you're actually going to spend more time trying to map all those together. And it's not always easy just to store that information just in the DOM. You think about things like nth child. Well, if you've stored all of your CSS information with each node, what happens when you modify the node? Then you have to shift all those around. So we map them together, and this is what happens. You have to do this, and you end up with a lot of time spent in formatting. So we've got a little bit of time here left, and we're going to go over animations really quickly. So if we look at animations, we saw that at the beginning. We just saw, this is just the same demo with running with 4 images. And all we're doing here is we're doing a set interval of 16 milliseconds. So every 16.66 milliseconds, we're going to go ahead and render the next frame. And if we look at the code for this, this is really simple. On the animation side, you can see what we're doing draw. We're just setting the X, Y, and Z coordinates for these basically, and wrapping them around, setting the styles. And of course, that's going to change the formatting for the page, or change the CSS cascade. Then we set the Z index basically accordingly. We'll update our FPS meter, etc. So as we start to do that, you can see that I actually do my set interval right here. Go ahead and turn that on. You'll see I'm just doing 1,000 milliseconds, which is obviously a second, divided by 60, which is my assumed monitor refresh rate. And that's where I get to 16.66 repeating for my time. So what I get is this nice clean animation. And I'm going to go ahead and load the trace for that and show you what an animation looks like. So we should get a lot of the same behavior that we saw before, the page load behavior. But now I'm just going to zoom in and look at the animations. So as I look at these, you can see what's happening, and I'll just select 3 here so it's easier to see. That what we get is we get a pattern that emerges in our animation. Every time we get a vsync operation here, a vsync interrupt, we go ahead and we ask layout. I'll just zoom in here. We'll ask layout, are we clean? Are we ready to display? And you'll see that right there. And we'll say, no, we don't. We have new CSS information from the last time. Our JavaScript modified the CSS, so I have to format. So layout says we don't have a clean display tree. Let's go ahead and do format. Now we'll lay that out based off of the new formatting information. Then we'll display. With the time that's remaining after display, you'll see this tiny little sliver of orange. That's just your JavaScript or your next set interval draw code executing. So we'll see formatting, layout, display, JavaScript. Formatting, layout, display, JavaScript. Over and over again. Every time we hit a vsync operation, that's exactly what's happening each and every time. So if we just scroll through here, you'll see these almost look exactly the same. I'm scrolling across the page, and they all look different. All right, they all look the same, sorry. So this is essentially what's happening, and this is how an animation occurs. Now, what happens if I decide to change my draw time from 16 milliseconds to 4 milliseconds? If I look at that trace, again, well, let's look and see what happens when we visit the page first. So set animate. Wow. Everything just got really, really, really fast. That must be a performance optimization. It's fantastic. Ship it. So what's happening here? We're updating the page more often than we can display to the screen. The screen can only refresh at 60 hertz. So we're calling JavaScript multiple times per frame. If we look at this in a trace, and we'll go ahead and get rid of this. Just zoom in and allow you to see what happens in between these. So you see we get the typical formatting, layout, display, JavaScript. Then a few milliseconds later, we get JavaScript. A few milliseconds later, we get JavaScript. And then we'll go ahead and do formatting, layout, display again, and we're going to do JavaScript, JavaScript, JavaScript. What's the point of that? The point is that we're doing a lot of work that never gets displayed to the screen. We're waking up, we're setting a timer, we're doing all kinds of work that we could actually save ourselves time with. We could actually go back and multiply the work times 4 in our set interval and get rid of the the set interval of 4 milliseconds and save ourselves CPU time. Now this looks insignificant, but this will drain battery life. If you care about devices, you care about mobile devices, you care about tablets or anything like that, your users will stop using applications if they drain batteries. I've done it. I'm sure you guys have done it. So this is one thing that you need to keep in mind. The performance is not just how fast you can do things. It's not how often you do things. It's how efficiently you do them. So I'm going to go ahead and skip one of the traces, and that's just request animation frame, but I do want to speak to it. This looks very similar to what we had with set interval. It looks like the same thing's happening. If we look at the trace, it'll look nearly identical. So what's the point? Why not just use one or the other? Why not just use set interval? Why do we need request animation frame? Well, it goes back to that assumption that I made. The assumption is that we're always running at 60 frames per second. What if your monitor's only running at 50 hertz? What if you're on a display that drops that down dramatically? Then again, if you're just setting a set interval of 16, you're doing the same thing as set interval 4. You're doing work when you shouldn't, instead of doing work how often the monitor can do it. So request animation frame allows us to set our timers more opportunistically based off of what hardware you're on. So set interval is nice, but if you're trying to do animations, I highly recommend that you use request animation frame. I would show you the difference here, but unfortunately, if you change you can't change the refresh rate while we're on display. That's okay. So that's what happens with request animation frame. I want to take a look at what happens now, as we start increasing the number of images on the screen. You'll see I'm at 64 images here. I can go to 60 frames per second. I'm still at 60 frames per second. I can keep increasing these images. I'm at 400 images, and I'm still at 60 frames per second. Once I go over that, I start to take a little bit more time than I have. So I start to fall over a little bit. I'm skipping a few frames here and there. You'll see it dip down now and again to 57. And that's just because I'm taking more time to do my rendering than I have in a single frame or have in a single between vsyncs. Of course, if I increase that even more, you notice that dip even more. So, again, if we look at that inside of a trace, apologize for the lag. This is just the 8x8. So we're not seeing it completely full, but in our last, if you remember when we looked at our first animations, they really weren't taking a significant amount of time in each frame. Now we can see that we're basically taking about a third to a half of that frame. We're taking about 7 milliseconds here. So, somewhere between a third and a half we're taking at that 8x8 matrix, so at 64 images. If we were to show you the trace where we're falling over, you'd see this frame is completely full. You'd see from here to here we would have CPU activity. It would be the same amount of CPU activity, but everything would take a little longer. Formatting would take a little longer, layout would take a little longer, and display would take a little longer. So the last trace that I want to show you is what happens when you do readback. Does anybody know what readback is? Raise your hand. Readback? Readback is what happens when you have an animation and you ask the browser a question. So you ask a browser a question about the element that you're animating. So I've just moved an element, and now I'm going to ask it, where am I? I've just moved it, and I just asked it. So that might be okay if you have one element that you're animating. It's still not going to be the most performant way that you can do it. But what ends up happening when you have a large number of images is you significantly reduce your animation time, and I'll show you why. Here's what happens. You notice we got up to 400 images before, and we can still keep it 60 frames per second. I'm doing readback in this sample, and you can see I've already dipped down to 46 frames per second. And that's just because I'm asking a question. For each element that I move, I'm asking a question about each of those elements. And I'll show you what that looks like in a trace. Once again, we don't need this. There's some really interesting things that are happening here. I'll zoom in a little bit. But we'll see, display happening here. Is this the right trace? Yeah. Oh, I'm sorry. This must be. Yeah, here we go. So we see our display. And in between each one of these displays, we'll see some other stuff happening here. We'll see formatting, then JavaScript, and then layout. And that seems a little backwards from what we're used to seeing from those other traces. And that's because we've done our display, and now we start to animate. So we'll go ahead and we'll do our JavaScript here. We'll go ahead and do our formatting that's based off of the CSS that we just changed. You remember our JavaScript changes the CSS. So we'll go ahead and do that formatting. But after we've done that, we ask a question. We say, what's the offset width of this element? And you can see that in the source code here. I'll go ahead and show you what that line does. This is it. I'm setting offset width, or I'm reading offset width. I'm not even doing anything with it. I'm just reading it. So inside the code, I've got this, this for loop, and I'm setting the left, I'm setting the top, and now I'm reading the value back. So I go ahead and then I read that, and what happens is because I've asked the question inside of JavaScript, I then have to answer it. And so in order to answer it, I go ahead and do layout. So instead of waiting to coalesce all of our layout and all of our changes together for that loop, we have 400 images, we're updating all that, and then waiting for the end of that next animation to say, let's coalesce all this work, and let's go ahead and do the formatting. For every image, I'm doing formatting again. I'm doing it over and over and over again, and then I finally get to display that to the screen. So if we could think back to our mental model of the web platform architecture again, we're doing JavaScript, we're going ahead and we're doing formatting, and then we say, hey, you know what? I need to read this value again. So we're going back to JavaScript, and JavaScript says, I need this value. So we go all the way back through again, do layout, we do a layout pass, and then our animation goes to the next element and does it all over again. It moves the next element. It says, hey, I'm changing formatting. I've done formatting. I have to do layout. JavaScript asks the question, where am I at? I have to do that all over again. And then, so basically for each element on the screen, I'm doing what I should be doing on an animation cycle. So it's just wasted work. If you can, if you need to, the best way to fix that is by simply creating a model and keeping track of where your content is and updating that on request animation frame. So this is the Web Performance Toolkit. Switch back over here real quick. Or the Windows Performance Toolkit, excuse me. I'm sure the team would love me calling it the Web Performance Toolkit. But in summary, you know, this is the thing. Is we have to understand the web platform. We have to get that mental model of how your content's moving through the system. If you want to concentrate on performance, you have to really understand how your content is executing in each one of the subsystems. The Windows Performance Toolkit is extremely powerful. I only showed you a subset of this today. There's a number of other talks today that I would highly recommend you either check out today or watch online once they're posted, because there's a ton of information that you can get out of these tools. We don't have time to show them all in an hour session. I would encourage you, if you get a chance, to go back and look at our 50 tips and tricks talk from last year. Last year we gave 50 tips and tricks. But here's the thing, is now you've got the tool to be able to say, here's my site, now I'm going to apply those 50 tips and tricks, and let me go measure again. You'll be able to see the performance difference. I highly recommend you do that if you get the chance. Here's our additional talks. I think you've probably seen this slide a couple of times. And we've also got some resources out here for you to be able to download the Web Performance Toolkit, get some other books that are really good about to explain patterns and anti-patterns and things like that. If you have any questions, feel free to tag me. I'm on Twitter. You can hit me on email. I'm more than happy to answer questions. I'll be up here afterwards as well. Thank you very much.